In this lecture, we're going to continue studying graph theory, and in particular, we're going to get into more detail concerning spanning trees and spanning forests, and discuss applications and how to solve the problem of finding spanning trees and spanning forests. Let's now take a look at Prim's algorithm and see how it accomplishes basically the same thing as Kruskal's algorithm, but in a substantially different way. Unlike Kruskal's algorithm, Prim's algorithm begins by focusing attention on some particular vertex. But when I say particular, it really is an arbitrary vertex. Okay? So just assume that we've arbitrarily selected some vertex from a connected graph to begin with. Okay, it's best to think about subgraphs again. In order to follow Prim's algorithm, it really is very helpful to visualize in terms of subgraphs. But, and this is a big but, unlike Kruskal's algorithm, let's not begin with a subgraph that includes all the vertices. Okay, in fact, let's begin with a subgraph that only includes this one vertex, right? This one selected vertex, and has no edges. Okay, so that will be our initial subgraph. Okay, and then the idea is going to be that we will keep selecting edges so as to grow that subgraph, and at each stage along the way, the subgraph that we grow will in fact be a tree. Okay, in Kruskal's algorithm, what we grew was a forest. If you think about it, the subgraph was not connected, right? Initially, it was very unconnected. With the Kruskal's algorithm, we grew a forest, and eventually we kept adding edges until it got connected, and at that point, it became a tree. But with Prim's algorithm, we're going to start off very small, one single vertex, and we're going to keep growing this thing, and we're going to maintain it as a tree. So our subgraph will always be connected. Okay, but just like with Kruskal, we have to be very careful as we add edges that we don't introduce any cycles. However, because we're maintaining this tree, a tree, there's only one connected component. Deciding whether we're adding a cycle or not is going to be absolutely trivial. We won't need the fancy test that we had concerning connected components and all that for Kruskal. Okay, so this subgraph we're considering is not spanning. And all we're going to do is, well, we're going to select edge of smallest possible weight, but subject to a slightly different requirement than before. Instead of selecting an edge that doesn't introduce a cycle, what we're going to do is select an edge that connects our subgraph, which is a tree, to some vertex that is not yet a part of the tree. Okay? It's as simple as that. So we simply have to take an edge such that one of the vertices is in the tree that we're growing, and the other vertex is not in the tree that we're growing. Okay? And if we choose the edge of least possible weight subject to that criterion, then we'll be following Prim's algorithm, and pretty much that's it. We just keep growing that small tree until it spans the entire graph. If we're started with a connected graph and we knew it was connected, and we knew that what we were growing eventually would become a spanning tree, that would be the end of the story. But for the moment, let's suppose that we have an arbitrary graph, and what we're trying to get is a spanning forest, right? So one spanning tree per connected component. So here's the deal. We really have to decide when it's time to stop. And actually, if we get to this stage where we can no longer add an edge to the tree that we were growing, right? That basically means that that tree that we grew is now a spanning tree for the connected component of the graph that it's inside, right? But there may be another connected component to the original graph. And if that's the case, then we should go and grab a vertex from that other connected component and then start all over again, basically growing a tree inside that component, okay? And when we get that done, if there's any vertices left over that we didn't cover, then grab such a vertex. It would have to be in a different connected component and grow a tree inside that one. And this process repeats until we've used up all the vertices. Okay? At that point, it's guaranteed that what we grew is not only a spanning forest, but in fact a minimal spanning forest. Let's try Prim's algorithm out on the example we had of cities earlier. Okay, so for no particular reason, I'm going to start with the vertex Mumbai. And this means that I'm going to begin with the subgraph that consists only of that vertex and no edges. Okay, now I have to look around for an edge that connects Mumbai to something else, right? And in doing so, I want to select an edge of least possible weight. Okay, so it turns out that of all the edges connecting Mumbai to something else, the one that connects Mumbai to Beijing has the least weight. So we select that edge and we grow our subgraph now so that it includes Mumbai and Beijing and the edge between them. Okay. And now we just iterate that same process. We're now looking for an edge that will connect our subgraph to something that's outside of our subgraph. So again, our subgraph just consists of Beijing and Kyoto. No, excuse me, consists of Beijing and Mumbai. It consists of Beijing and Mumbai and the edge between them. And as we look around for edges, we find that there's an edge that connects Beijing to Kyoto, and it has the least possible weight among all the edges that will connect our little subgraph to a vertex outside of it. Okay, so we select that edge. Okay? And we continue like this, and the next edge that we select will be the one that connects Riyadh to Mumbai. Why? Well, just look around and check out all of the edges that connect either Mumbai, Beijing, or Kyoto to something else. And of all those edges that do that, the one that connects Mumbai to Riyadh has the least weight. So we select that edge, and then Riyadh becomes part of our subgraph too. All right? And if we just proceed like this, as we continue, that subgraph that we're building is a tree, right? And because our graph, our original graph was connected, the original graph is connected, therefore the tree that we're growing is going to eventually span the entire graph, at which point we're going to be done. Okay? So we're going to be encouraged to continue this example. And I say the original graph was not connected, then after we've grown a tree that spans one connected component of the original graph, we would just continue into some other connected component and grow a spanning tree for that connected component and keep going like that. And then all these spanning trees, all these trees that span the connected components together form a spanning forest. And in fact, it will be guaranteed to be a minimal spanning forest.